Sir, post permission கொஞ்சம் கொடுக்குறீங்களா sir?
மேம் கொடுத்தாச்சு மேம்.
Okay sir. Okay sir. Screen visible இருக்குல்ல sir?
இருக்கு மேடம்.
கிளியரா இருக்கு.
Yes sir. We'll just see the review of what you have seen in the earlier class. We started with the introduction of the steam, where it is used and why it is used, because it is having the high specific heat and latent heat and the highest heat transfer coefficient compared with the other fluids, and the other properties of steam, the conversion of solid to liquid, liquid to gas, where we will be focusing only with water to steam. So this is the common equation where the ice is being converted into water. So here we have come across a heat term called latent heat of fusion of ice. And further heating of water, it will be converted into steam at atmospheric pressure, and the heat added will be equivalent to the same equation where the specific value will be the specific value of water multiplied by the difference in temperature. And the further addition of heat will convert the water into steam. Another new term here will be the heat involved in this process will be called to be the latent heat of vaporization. And further addition of heat will convert the steam into superheated steam. And again, the same formula will be used where the specific heat in this case will be the specific heat of steam. So here we have come across three specific heat values. One will be the ice, other one water, another one will be the steam. And del T will be the difference in temperature in all three cases. And the corresponding TH plot is what you have seen in the last classes. You have considered taking a heat at minus 25 degree centigrade. If it is given heat, what happens till 0 degree is furnished, and again at 100 degree what is happening, and again further addition of heat is making it to convert into steam. So this is for one particular pressure. If you are going to draw for different pressure lines, here see this is the line shown in blue, red. This shows the for a particular pressure. So if this is drawn for many pressures and the process is repeated, this dome is created, liquid vapor dome. Whereas this point, this curve is attained by joining all the saturated water points. And that's why this curve is called to be the saturated water curve. And whereas the other side, the point C, I hope you all do recall it. See, the process here is B and C. So this is for one single pressure. If the pressure is raised above atmospheric pressure, the line BC gets converged, because due to higher pressure, the temperature, the heat addition required will be lesser. So this BC will try to converge and it will form a vapor dome like this. So in this area, it will form like this, and that's what is shown here, liquid vapor dome. So this is the point where the critical, it is called to be the critical point where the saturated water and saturated steam curve meets. That means at this particular point, there won't be any intermediate phase. That means we won't have the wet steam at all. The water will be directly converted into steam. Instant conversion of liquid water to dry steam will be there at the critical point. And above critical point, if you are going to increase the pressure, instant conversion will be there. That is what is the base for the supercritical boilers. And what is happening in this dome is you will have a two-phase mixture, water and steam. And this is what is seen in this diagram. So this is given in a textbook also. The points A, B, C, D. This is drawn for a particular pressure. And if you take this line B and C, the point B represents the quality of steam. You introduce a newer term called dryness fraction. So at point B, the dryness fraction X is equivalent to 0, which means there is no steam available. Only saturated water is available there. Further addition of heat will convert the saturated water to steam, and this is what happens in the line BC. So if you take this point B, there won't be any steam, but it will be in a stage to get converted into steam. If you add 1 degree of heat, then it will be getting converted into heat. So it goes on until point C is achieved. So at point C, there won't be any liquid water.
Ma'am, what happened, ma'am? No slides, ma'am.
I think there is some network problem, madam. Wait, just reconnect it.
Okay.
Yes, and it's reconnected. I'll continue, sir. It is connected again. Shall I continue?
Yes, ma'am, you can proceed.
Yeah. So this point B is where there won't be any steam, and the point C is the place where there will not be any water. So this goes on as the pressure increases, it creates a dome. So these are the lines of constant pressure. And from this steam phase diagram, we can observe whatever present outside this dome, that is to the left side, you have the saturated waters. And whatever is present after the dry saturated steam line will be the superheat steam. And in between will be the wet steam. So here three kinds of steam we have. One is the dry steam, which will be on this curve. And inside this, you will have the wet steam. And after beyond the dry steam, you have the superheated steam. And the wet steam is qualified by a term called dryness fraction. That's what we have seen in the last class. So the value of X, it varies from 0 to 1. So we call it to be the quality of the steam or the mass fraction of the vapor and the liquid vapor mixture. So this is the liquid vapor mixture line, B and C. And three kinds of properties arise here from this graph. One is the liquid enthalpy, or you call it to be the formation of enthalpy from the in the fluid state. That is why you use the term of suffix F. So whatever energy spent in the water till the boiling point is reached. So that heat is called to be the sensible heat, or you call it to be the liquid enthalpy because it is in the liquid state. And another term is called to be the enthalpy of evaporation. In other words, you call it to be the latent heat of evaporation. So here the phase change from fluid to gas occurs. So that's why the term HFG, suffix FG is there. So here there won't be any change in temperature because you have the change of phase from liquid to vapor. And here a new property called saturation temperature is introduced. So saturation temperature is the corresponding temperature on the point C. So where water boils, so here two saturation temperature occurs. One will be at the point B, another one will be the point C. And a third heat will be the enthalpy of saturated steam, Hg. So it is at the point C. Since all this water would have been converted into steam. So it will be the summation of Hf plus X into Hfg. So this you can find it here in the same graph. This point C, if you're going to draw a line, this will be the Hg, which will be equivalent to the summation of Hf, the heat, sensible heat added in order to increase the temperature of water from point A to B. So this is the sensible heat. And here B to C is the latent heat of vaporization. And the total heat enthalpy is called to be the Hf. So from the graph also we can take the value. And this is another temperature termed to be the degree of superheat. So beyond the dry steam, if you are going to add heat, whatever may be the heat added, it is spent in raising the dry steam into the superheated steam. So how much heat you are going to give in? So that you call it to be the degree of superheat. So in the vapor dome, what you have seen here, the same, these are the highlights of the vapor dome. So what I have already seen, that is the saturated liquid line and the saturated vapor line. They enclose a region. So where you call it to be the wet steam. So steam water mixture exists there. And in the region left to the saturated liquid line, only water will exist. In the region right to the saturated liquid line, only superheated steam exists. So both meet at a point where you call it to be the critical point. So critical point is 374.15 degrees Celsius and the corresponding pressure is 222.2 bar for steam. So above this pressure, we term the steam to be the supercritical steam. So this, we can find the values in the steam tables. So if a problem is given for us, the corresponding pressure is there, corresponding temperature you can read from the pressure, and HF, HFG and FG, all you can read it from the tables for working out the problem. And this is steam distribution. So we have generated the steam. After generating the steam, it has to be properly distributed to the end user. So the starting point is the boiler and the end point is the turbine. So from the boiler to the turbine, the steam has to be evenly distributed with the corresponding pressure, the right quality and at the right quantity. Quality here refers to the dryness fraction, and quantity, it is the mass flow rate. So that is the main aim of the steam distribution system. So this is the essential link between the steam generator and the steam user. So the purpose of this is to give it at the right quality and pressure at the right quantity. So of course, at the installation time itself, the care will be taken that the proper steam distribution is followed. So as the steam condenses in the process, a flow is induced in the supply pipe. So once the steam has done its work, the second process will be the condensation. So as it is getting condensed, so again phase change from vapor to liquid happens. So there a driving force is induced due to the vacuum because the pressure will become low. So that pressure drop causes the flow in the pipe. Okay, so it's reconnected.
Yes, madam. Yes, madam.
Yeah, continuing, sir. So this is the steam distribution system. So steam distribution, thereby the steam generated in the boiler, it should be conveyed through the pipe work. So we have a front user, that is the boiler, and we have an end user, that is the turbine. So intermediate, we have the pipelines to connect this boiler to the turbine. So in our power plant, there will be one or two steam mains. So where the steam is being conveyed from the boiler into the turbine. And also there are some other branch pipes which carry the steam to the individual equipments. So the main criteria in the steam distribution system is the working pressure. So even though the distribution pressure of the steam is influenced by a number of factors, it is mainly locked by two factors. One is the maximum safe working pressure of the boiler, other one is the minimum pressure required at the plant. So pipe work, it will have some pressure loss. So it will be again due to the main two reasons. One is the frictional resistance that is occurring within the pipe work, and the other one factor is the condensation that happens within the pipe. So that is as heat is lost to the environment. So this is the general layout of the system. So in order to have a good layout and location of the steam consuming equipment, this is of the great importance in the efficient distribution of steam. Why we have to take care of this layout is wherever the shortest possible distance is there, the frictional loss will be minimum. So then and there, the steam pipes will be laid with the shortest possible distance. Other things that comes into the design will be the aesthetic view, architect plan. So all we need to have a compromise between all these. So this happens only where we are going for a process industry. But in a power plant, the layout is already fixed. So the next factor which comes into the steam distribution system is the steam pipe sizing and design. So which directly affects the quality of the steam, pressure and quantity. So any modification in the system will affect all the three. So the pipe sizing is very important to make the steam deliver at the correct pressure. So pressure drop through the distribution system, which is very important feature because it is the driving force for the flow to happen from the front user, that is boiler, to the turbine. So proper sizing is important in minimizing the pressure drop. So the velocities and for the three kinds of steam is given is based on the correlation value for superheated, saturated and wet. So another one is the pressure drop in the steam pipe. So here we may be in a position to do some problem. So if you are going to take a steam pipe with a flow velocity of U with a pipe diameter of D, take 0.1, which is at a height of the datum level is at H1, and you take after a length of L, you take another 0.2, which is at a height of H2. If you take the energy level at 0.1 and energy level at 0.2, there should be a energy level higher in the 0.1 than at the 0.2. This difference in energy level will overcome the frictional resistance and it will cause the fluid to flow from the 0.1 to 0.2 in the positive X direction. So this is the principle in the steam pipe. for the flow inside. So this is again given by the equation. HF is equal to 4FL U square by 2GD. So based on this equation, problems may be asked. So HF is the heat loss to friction. F is the friction factor. It is always in the form of chart or it is a tabulated one. And in our case, the value of friction factor will be given in the problem. And L refers to the length of the pipe. U is the flow velocity. G is the gravitational constant. And D is the pipe diameter. So this is head loss, which is proportional to the velocity square. And friction factor is an experimental coefficient. So it is affected by many factors, but the main one is the Reynolds number and the reciprocal of the velocity. So based on that, we have discussed a problem. Hope we do remember this. In the last class, we have worked out this problem. So this type of problem is asked in the question paper also. So here the difference in pressure is HF is asked to find out. Between any 2 points, the point's distance is 1 kilometer. The length of the pipe is given to be 1 kilometer. And it is a horizontal pipework system. The water flow rate is given. It is in meter cube per hour. And temperature is given. Friction factor is given to be 0.005. So that is what is taken. So in order to find out HF, you have to use this formula. 4FL U square by 2GD. And here U velocity, we need to convert it into meter per second. So it is given in, the flow rate is given. So we convert it into meter per second. That's what is done here. So 45 meter cube per hour, we divide it by 3600 and you get it in meter per second. And similarly, the area. So if you substitute in the formula, you get the pressure value. And this is another problem. This is also a solved problem in our textbook. So this is to find out the pipe size, the diameter. So here the process requires 5000 kg per hour of dry saturated steam. So it is the mass flow rate given in kg per hour. So you need to convert it into kilogram per second. Then it is a dry saturated steam at 7 kg per centimeter square. So at the 7 kg per centimeter square, we can read the specific volume from the steam tables. It is equal to 0.24 meter cube per kg. And we need to find out the size of the pipe. That means diameter of the pipe is to be found out. And flow velocity is given. It should not exceed 25 meter per second. So the same formula, we are going to rearrange it. And if you're solving it, it comes to 130 mm. So 130 mm, the standard nearest commercially available size is 150. Then the other topic is the pressure reducing de-superheating station, or we call it to be the PRV. You have a pressure reducing valve and we need to reduce the steam pressure sometimes when the temperature rises beyond it. So that process we call it the de-superheating. So this is actually done by spraying the water through a nozzle, either automatically, and once the temperature is attained to the required value, reduced, then we stop the spraying. So this is proper air venting. So while the steam is given inside and the flow is there, along with the steam, some condensable gases come along with the steam, and also some air gets involved. So it needs to be drained out then and there. Otherwise, this will result in the reduction in efficiency. So proper air venting should be given. Then and there, almost in the main pipe at the end point, the air venting is given. So this problem is showing us that the temperature of the steam is getting reduced. So 158 to 152. So this is the effect of air if it is present in the steam. So other one is the steam pipe insulation. Why it is done? The steam pipe which is carrying the steam should be insulated well. The reason is it reduces the heat loss, facilitates the temperature control, prevents the condensation of steam inside the tube, and it reduces the damage to the pipe, and the surface control temperature is not allowed to raise. So this is where we stopped in the earlier class. So now with this, we go into the efficient steam utilization. So the steam has been generated. What has been generated is distributed with the help of steam distribution system. Now it has been efficiently utilized. So that is the second part of the after distribution. First one is the generation, other one is the distribution, then you have to utilize it. So in the steam system, the major scope for improving the energy lies in the utilization part. So the steam generation and the distribution efficiency, they are very much higher than the utilization efficiency. So generation and distribution efficiency is almost 80%, whereas the utilization is only 47. So it is similar to we get we get the salary, we distribute it for certain things, but we utilize it only lesser. It is equal to. Then why to go for such a steam? We can use some other fluid, is it not? So this diagram shows the steam system efficiency. So here the fuel is burned, the chemical reaction occurs, and 100% conversion, and the efficiency is considered to be 100% because there is not so much of loss to the environment. But this is the generation part, steam generation part. So in the boiler, around 20% is lost, efficiency is lost. There is some reduction, and around 80% will be the generation efficiency. So this region is the generation part of the steam. So this is the steam mains, where there is some loss. Again, it is distributed to the process. Okay, the distribution efficiency is also 83%. But when it is utilized, when it is finally converted into product form, that means when the heat energy is utilized from the steam into a useful work, that utilization efficiency, after considering all the losses, is only 47, around 47. It is only equivalent to 35. So why to go in for such a kind of system? Only even it has, since only the efficiency is very less, overall efficiency is 35% only. Then we can go for any other working fluid instead of steam. There may arise a question. So the answer is the steam has superior properties which is not offered by any other heat medium. So the main notable property, because there will be instant conversion of the temperature. So instant conversion, and the steam has the tendency of giving the even heating, and the heating is also very quick compared with the other fluid. Suppose if we are using a hot water to convey the heat, the process is very slow compared with the steam. So these two reasons make the steam to use in the utilization of heat. So this is here designated with the help of a TP plot. So say for example, if you know the steam pressure, in the case of a saturated steam, the steam pressure is known. The corresponding steam temperature can be determined. And if in this case, the steam condenses. So here, if you're going to take the steam getting condensed, what is happening here is it condenses at the same saturation temperature. So at the saturation temperature, there won't be any change of temperature. The pressure at the heat transfer surface will be constant. So that you can see in the curve. So this is a constant pressure line. And this is the reason why continuous heating will be able to take place. So the temperature will be the same and heating will be continuous. So this is where is the main criteria why we choose steam to be the working fluid. Okay. So this is what is indicated by
Screen vanished, ma'am. Screen.
yeah, sir. There is some disturbance in the net. That's all.
Okay, now.
So this is what is indicated by the heat transfer coefficient. So the unit is watt per meter square Kelvin. So if heat exchange takes place on the same heat transfer area with the same temperature difference, larger will be the heat transfer rate and shorter will be the time. So this is the reason why we go in for the steam to be the working fluid rather than so many fluids are available. But the reason is the heat transfer rate will be larger with the shorter time. So this is the heat transfer with steam. Say it's a heat exchanger. So high temperature. This is the product inlet. This is a heat exchanger. So the green one is the product at a lower temperature and product at a higher temperature is at this particular. So as it gets so higher temperature flows here, heat gets exchanged, and at the outlet it is getting converted into a product at a higher temperature. Whereas it is entering into the, this is the inlet. It is giving its heat to the other fluid with the help of this through the conduction mode, and then it is getting exhausted here, and the condensate is collected at the outlet. So this is the simple process of heat transfer with steam, say a heat exchanger. So here the tabulated values for the heat transfer rates for hot water and steam, they are given here. So the rate at which the heat is transferred to the heat surface, from case of a heat exchanger, if you take in, it is a hot water, the value is 1000 to 6000 watt per meter square Kelvin. Whereas if the fluid is working fluid is steam, the same heat transfer rate is equivalent to is between 6000 to 15,000. That means it is around 2 times higher. If you are going to use hot water as a working fluid, the heat transfer rate is only up to 6000. Whereas here steam, it is around double the heat transfer. So in actual practice, if you take, this is a heat exchanger where this is a shell and tube heat exchanger. So this is the shell, and inside which you have a tube. So in the shell, hot fluid enters and it is giving its heat into this tube and coming out as a cooled fluid at a temperature of TF2. Whereas inside the tube, the cooled fluid is sent inside, and there is some heat transfer here, and it is taking up the heat from the hot fluid, and the warm fluid is coming out. So here we need to study about the mechanism of heat transfer. So the combination of the heat transfer will be the two. One will be within the wall of the heat exchanger. Another one will be the mechanism of heat transfer from wall surface to the heat exchanger to the product. In other words, you can say first form will be the conduction point of heat transfer. So from the wall. Another one, convection within the fluid. So you have to go back to the early heat and mass transfer basics, where we might have come across a term called the overall heat transfer coefficient. So here we just recall. So this is a slab, say, of thickness del X with a thermal conductivity constant of K, and say, for example, at the other side, the fluid is at a temperature of TA, and what happens thickness of and also convection is there. In both the sides you have the convection, and in between you have the convection. So that is what is designated by this thermal network. So the temperature TA is one node to be found out. Another one is the temperature T1, that is the fluid temperature, the temperature at this point. And T2 is the wall temperature at the other side. And TB is the temperature at the right side. So if you take in the overall heat transfer coefficient, we have to use the formula. This is by convection, this is by conduction, and again so again this is applied for a heat exchanger. So this is a shell and tube heat exchanger where the temperature at the shell side will be TB, and inside the tube it is TA. So the same is given in the form of apply Fourier's law of heat conduction. So that is what is applied here. So all these has to be considered for utilizing the steam. That is what is the concept here. So types of heat exchanger, we know there are very wide varieties of heat exchanger depending upon the flow. So whether it is co-current flow or counter current flow, cross flow or cross counter flow. So whatever may be the types of heat exchanger, the overall heat transfer coefficient has to be found out by using these thermal network. So we will arrive at the overall heat transfer coefficient, and then we will decide which type of heat exchanger can be used for optimum utilization of the steam. So the steam provides the rapid heating because the transfer of heat is caused by the process of condensing. So once it is getting condensed, as we have seen earlier, it is the driving force. So the latent heat contained in the steam is released instantly, so which is much greater than the sensible heat. So if you take a hot water for getting the heat energy transferred, it will be only the sensible heat. But if you take the steam for the same process, it is the latent heat. So when you compare latent heat with sensible heat, the sensible heat will be much lower and the latent heat will be higher. So again, this is the main reason where we go in for the steam as the working fluid, even though the utilization efficiency is very low. So that is what is given here. Hot water and oil are used in convective heating, but they don't involve a phase change. So no phase change means there is no latent heat of vaporization involved there. So latent heat of vaporization means higher amount of heat energy. So here the heat medium reduces its own temperature in order to transfer heat to the product. So reduction in temperature and rise in temperature at the other end. So there, in order to increase this kind of efficiency, normally when a working fluid of hot water or oil is used, we use a forced convection method, but by externally powered pump to create the flow and increase the heat transfer. So we'll do one problem. So steam jacket atmospheric pressure. The kettle has a 680 kilogram per batch capacity. Milk is heated from a temperature of 26 degrees to 100 degrees, where 25% of its mass is then driven off as vapor. Determine the amount of 1 kg per centimeter square steam required per batch, not including the heating of the kettle itself. Specific heat of milk is given as 0.9 kilocalories per kilogram degree Celsius. The latent heat of steam at the pressure of 1 kg per centimeter square is 525 kilocalories per kg. So this is the problem. We need to find out what is the quantity of steam required. So we start with the quantity of water evaporated from milk. So the kg given is 680, out of which 25% is driven as vapor. So quantity of vapor evaporated from milk can be found by multiplying the kg with the percentage. So 680 multiplied by 0.25. This is 25% of the mass. So 25 by 100, we get 170 kg per batch. Next step, we need to find out what is the heat required to raise the temperature of milk from 26 to 100 degrees. So this is the sensible heat for raising the temperature from 26 to 100. So mCp del T, the same formula. So m is mass, that is 680 kilogram. Specific heat of milk is given to be 0.9 kilocalories per kilogram degree Celsius. So into 0.9 into difference in temperature. So difference in temperature is in order to raise from 26 to 100. So it is 100 minus 26. So mCp del T. If you calculate it, if you have calculator, you can also calculate. So it comes to around 45288 kilocalories per batch. And third step is to find out the amount of heat required to evaporate 170 kg of water. Because here we have found out what is the quantity of water evaporated from milk. It is equivalent to 170 kg per batch. So for evaporating this amount of water, we need to find out the heat. So which is equivalent to, because here a phase change occurs. So this is M into L. So L is the latent heat of vaporization. It is 540. So 170 into 540, you get 91800 kilocalories per batch. So this is the sensible heat. This is the latent heat. So the total heat will be the summation of sensible and latent. So it is equivalent to 45288 plus 91800. So the total heat accounts for 1370.88 kilocalories per batch. So what is the quantity of steam required? We need to multiply it by the kilocalories per kilogram. So much of kilocalories per batch is required. So in order to find out the steam required, we need to divide it, So when you need to divide it by the latent heat, so that you will get in kilogram per batch. Quantity of steam required will be 261 kilogram per batch. So these type of problems are asked in our question paper also. So first step is we need to read the problem. We need to find out what is given and what is asked. Then we need to arrange it in order. The same formula will be there, but accordingly we have to use it and we have to get the final answer. Okay, sir. The other one is the thermocompressor. So thermocompressor, as the name indicates, it is a compressor is utilized in raising the working fluid pressure from P1 to P2. Thermocompressor means it is the compressor involved with heat. So it is working with heat. So here thermocompressor, in the utilization part, where the condensate comes out at higher pressure, a large amount of portion of the steam is getting wasted as a flash. So into a low pressure steam as it is driven. In order to overcome it, what we do is you use a thermocompressor and we compress this lower pressure steam with the help of a higher pressure steam. That higher pressure steam might have been taken from any other point. And we mix the higher pressure steam and the lower pressure steam in a mixing chamber. This is the mixing chamber. And we reuse it as a medium pressure steam. And what is the use of this? It is just a form of waste heat recovery. That's all. So that is what is given here. The higher pressure motive steam, they enter in the lower pressure steam and increase its pressure. So it is introduced in the nozzle of the thermal. The nozzle purpose is to raise the pressure because it will enter a converging portion. So the whatever enters inside, as the nozzle open, the high velocity motive steam draws the low pressure. And you have a combinal effect of the high and lower pressure. A medium pressure steam is formed. So in other words, you say there is exchange of momentum. So this mixed flow, this enters the diffusion section and the velocity of the mixed flow is reduced. As the velocity is reduced, pressure will increase. So this is PV is constant. So based upon this principle. So where it is applied, it is normally applied where boiling steam is recompressed. There where it is used. So it's just a introduction to thermocompressor. It may be asked as a 2 marks question or 1 mark. So what are the advantages of thermocompressors? Here, there won't be any condensation loss. So it will be because there won't be any sudden conversion of higher pressure to lower pressure. So that losses will not be there. And since we are mixing the waste heat recovery is there, thereby the thermal efficiency will be higher. So there will be some savings of the system. And since the pressure conversion happens in the form of in the nozzle, there won't be any minimum. Operational charges will not be a major one. It is a low space is needed for because it's a simple nozzle and diffuser form only. Fouling will be lesser, and thereby, if you combine everything, the operating reliability will be higher. So, with this, we close today. So, what you have seen in this class is the steam distribution system, which is utilized steam utilization system, and the problems based on that. So sorry, there are some network problems, so sorry for the inconvenience. Any queries can be taken up, or leave it to Dr. Bala sir, please.
Interaction block. Click on answer, please.
Sir, shall we close it, sir? Any queries can be taken up, or we close the class?
You can close.